It's been a long time since we've recorded an episode.
Well, yeah. How long has it been? Let me check the dates on the files.
Go ahead and check the dates. Crunch those numbers,
Crunch those
Poindexter.
numbers. That's my name. It has been more than a month. It's been a month and a half.
Whoa.
We recorded
Really?
November 24th.
We didn't record anything in December?
No. Because it was end of
Oh,
semester
no.
for me, and then it was holidays for like 3 weeks.
You came home and Santa Claus visited you and said, why don't you have a microphone that works?
How nice. How nice of Santa. So thoughtful, that man. I tell you.
That's Santa. He's a good dude. I hear, at least. I've never met him.
Oh, really?
I've never been a good boy, so.
Oh. You're not at the mall? You never saw them? Pretty cool, dude. He looks different every time I go, though, so I don't know.
Curious how that works, huh?
I mean, the same vibe, same, like, general features, but, like, definitely different kind of face, you know?
Well, it's been a whole month since we recorded, and I've had some people actually clamoring.
Oh, really?
Yeah.
Hopefully
there are
not
people out there who've
too,
been like,
too violently.
when's the next reference frames episode? And I'm like, I don't know.
Well, you're in
I don't
luck.
write the script.
You're in luck, pal.
Guess what? Here we are,
Here we are.
back in business. We're kicking down your door and we're bringing you a podcast.
Oh, yeah.
That's right, gang. It's Reference Frames Podcast, the one where we take physics and make it more accessible by linking it to movie scenes.
Nice.
How was that for an intro?
That was pretty good.
Well, it's kind of like a one-sentence one.
Yeah, it was nice and concise, Real nice.
My name is Ian. I didn't write the script, and this is Will. He did write the script.
I did write the script. So,
And that's all we have to it. Normally we start with the corrections corner.
corrections. Oh.
It's been more than a month and we've had no corrections. As you'll recall, the previous episode was the Newton's second law, and we used Spider-Man,
Spider-Man 2.
specifically the second
Specifically
Spider-Man
the
movie.
first Spider-Man 2. There have been 3 Spider-Man 2s.
Correct.
In the last
Tobey
20 years.
Maguire, episode 2, Spider-Man,
Yes.
featuring Dr. Otto Octavius.
Such a tragic character.
Such a tragic character. If you want to learn about that, you can go listen to that episode. But that was the last one we had, and we had no corrections brought to our attention from it, which is sad because I was hoping someone would correct you on what that lever was in the train.
Oh, please, yeah.
To this day, no
Someone
one will ever
scrub
know.
through it really slowly. Get your magnifying glass
Please.
out.
Right. So in that case, oh shoot, what comes next? Oh, we basically just go right into it, don't we?
Right, yeah, we're a little rusty. I think we just hop right into it.
I'm a little bit rusty. Well, why don't I turn the floor over to you, Will?
All right. In the 29th century, the lone inhabitant of a garbage-strewn Earth is a waste allocation load lifter Earth-class robot, or Wally for short. He is the last remaining trash compacting robot created to clean up the detritus and debris created by rampant consumerism and corporate greed 7 centuries ago. His adventure begins when he finds both a small seedling growing inside of a boot, as well as a highly advanced extraterrestrial vegetation evaluator robot, aka Eve, sent by the humans now living aboard a colossal starliner. He eventually ends up aboard the Ark-like ship, but the seedling is stolen by its scheming autopilot AI and is sent to an escape pod to be self-destructed in space. Wally manages to make it aboard the escape pod, but it's jettisoned into space with limited time before the pod is set to explode. The robot just barely manages to grab a fire extinguisher from the pod and escapes in the nick of time. As Eve is desperately flying through space to try and find her friend in the remains of the pod, Wally comes whizzing out of the wreckage past her, firing the extinguisher behind him all the way. A beautiful scene then unfolds, where Wally and Eve dance through the night sky, one partner leaving behind a stream of extinguisher foam, the other a blue ion glow. To slow down, Wally blasts the extinguisher in front of him, and then to speed up or change his trajectory, he points the nozzle in the opposite direction of wherever he wants to go. The foam particles shoot off in one direction, and our favorite robot zooms the other way. Their joyful pirouettes cause some on the ship to marvel at the odd pair zooming around beyond the large windows of the ship, as audiences everywhere in theaters smile ear to ear at the adorable robots falling in love. All right, Ian, there's a scene. What's the what do you think the concept for this week is?
Wally. That was that.
I love that movie, dude. I love that movie so much.
So
I just
good.
rewatched that scene. I was writing the script, and man, and maybe you want to rewatch the whole film. That movie's so good.
It's a good movie.
Great movie.
It's a good movie all the way through. Boy, that AI robot, what a punk.
Otto.
So scary, too.
Yeah, just a big wheel. It's freaky.
Rocket science.
Rocket science. Is that we're yeah, it's just rocket science that we're talking about?
I'm trying to think of what else we could talk about here. I feel like it's a pretty clear-cut case of rocket, of kind of rocket physics, I guess.
Well,
Because I guess draw it even further back. Momentum, inertia, maybe. Momentum. I saw you perk up when I said momentum.
well, the audience can't see anything. But
Surely I'm getting closer.
no,
right?
you're basically on the money. You know, it's pretty clear, I think, from the scene. Yeah, we're talking about effectively rocket science, but yeah, I'll pare it down to a more the base concept involved in that, which is momentum conservation. All right, so basic idea of momentum
Hooray.
conservation. Conservation of momentum. First point I want to make, this is highly related, interrelated with the topic we talked about in the Spider-Man episode, Newton's second law. Very interrelated topics. Maybe you can talk about that at the end as well. But let's zoom out a bit before we get into the specifics of this concept in particular and talk about what physics in general is, because I think it's a good way of kind of getting into what we're talking about. So a lot of physics, or one fundamental idea present in physics, is this idea that you have some physical quantities, and if you combine them in the right ways using mathematics, you can create new quantities via the combinations of them that can have really useful properties. So in this case, we combine an object's mass, so how massive it is, how much weight it has if it's in a gravitational field. We combine that with its velocity, you know, how fast it's moving, what direction is it moving in. We combine those just by multiplying the two quantities together, and we get a new thing we call momentum. And you could technically combine anything you want together, but some of them are more useful than others. And momentum is useful, this straight up multiplication of mass and velocity, because that quantity, in the absence of any external forces, i.e. last week talked about external forces, in the absence of those forces, that quantity, that momentum, doesn't change. It can't change. And that's the conservation idea. So in the absence of any forces, this quantity called momentum will not change, which is very useful, as we'll talk about. So first, let's talk about what this actually looks like. What does it mean? How do you visualize momentum conservation? So the basic idea is if you are moving in some direction with a certain amount of speed, and nothing is pushing on you or pulling on you or affecting you in any way, you will keep moving in that direction at that same speed. And this is pretty easy to see with like an air hockey table. If you imagine those little pucks on the air hockey table, if you hit one, right, it goes in whatever direction it's going in at a pretty constant velocity in a straight line. And that's a classic example. There's very little friction on those tables. There's no real forces acting on it until it hits a wall or something. So it just moves in a straight line at a constant speed. All right. You follow me so far, Ian?
Yeah.
Cool.
This makes sense to me so far. Mm-hmm. I don't even really have a summary for it. I feel like the air hockey table example is really good.
Yeah. Basically, yeah. And it's maybe worth pointing out, this is different than what a lot of people used to think pre-Newton. Aristotle had a different idea of how motion worked. His idea was kind of probably a very enticing idea, is that everything wants to be at rest. And if it's moving, it'll eventually slow down to be at rest because that's what it wants to do. Newton says, no. Things want to keep moving in whatever direction they're going in. That's momentum conservation. Aristotle lived in a world with a lot of friction, so he just saw everything come to rest, so he assumed that was the natural way. But no, Newton says if there's no forces, they'll keep moving however they're moving. They won't naturally slow down without something slowing them down. How is it in this scene that Wally is changing his direction all the time? Even when Eve isn't touching him. He's whizzing around, changing direction, looping all over the place. He has no forces externally acting on him, right? There were two different ways of looking at it. We're going to look at one of them, which is about using momentum conservation to analyze it. All right. So maybe rewind a minute or two. Notice in the definition, yeah, thank you, Ian. In the definition of momentum conservation, I mentioned that a system's momentum won't change without an external force, right? I did little air quotes when I said system.
He did. I can confirm it.
Thank you. So if we look at Wally and the extinguisher together as one system, their combined momentum doesn't change, even though he's zipping around everywhere. And this is a little tricky to see, so let's think about it a little more. All right. Let's start by looking at a point in the scene where Wally's just stationary. He's slowed down, he's blown the thing in front of him, so he stopped in space. He's talking to Eva, maybe. When he fires off that extinguisher to begin moving, right, what's going on, right? He is moving in whatever direction he's going because he starts blasting off. But notice that a bunch of foam is flung out of the nozzle of the extinguisher in the opposite direction, right? So he's moving, let's say, to the left on the screen. That means his momentum is to the left. But all the foam is being blasted off to the right. And so that foam has momentum too. It has mass, it has velocity. Its momentum is to the right. And if you were to combine all the particles together, look at their total momentum, all combined, it would be exactly equal and opposite to Wally's momentum, to the left. You see what I'm saying there, Ian?
I see what you're saying, because he's throwing out a bunch of foam. The foam has momentum going in the opposite direction that he's going. And so it almost cancels out if you think about it.
Yeah, mathematically, it perfectly cancels out. If he was at rest beforehand and he shoots off to the left, all the things that went to the right must be exactly equal and opposite to his momentum to the left. You can also imagine this in space. If you're floating in space and you have like a wrench in your hand or something like that, if you just hucked the wrench in one direction, you would go the opposite direction because you and the wrench had no momentum, and therefore, once you throw it, you combined still have to have no momentum. It can't have changed. So the wrench will go off to the right, and you must go off to the left to keep the total momentum 0.
What movie is that? Is that Gravity? Doesn't
I
Sandra
think
Bullock
that's
do that in Gravity?
Yeah, you're thinking of.
How big does the wrench have to be?
As long as it has any mass at all, it'll send you moving. The more massive it is, the faster you'll go, because it'll have more momentum forward, so you'll have more momentum backwards. Because, you can only gain as much momentum backwards as you shoot out forwards. So if he shoots a bunch of foam out, he'll have more foam going, more momentum in front, so he'll be going backwards with more momentum as well. Does that make sense?
And a little tiny bit of momentum. A little tiny bit of foam.
He'll barely move.
A little tiny bit of movement.
But he will move, just not very much. Okay. All right, so
I'm following you.
Let's tie back into the scene now. So from the second that explosion ends, right, the pod explodes in space, from that point on, presumably Wally and the extinguisher have no external forces being applied to them, right? Aside from whenever Eve touches him.
Yeah.
That means that for the system, Wally, the fire extinguisher, and all the foam inside the fire extinguisher, that whole system, that will have the same exact momentum for the entire duration of the scene. So therefore, all the scenes combined should have the same mass times velocity-ness for the entire scene, even though Wally's zipping all over the place. The thing that's complicating it is that this foam is going all over the place too. And it's going all over the place in the exact same way to cancel out his motion, effectively. So in order for him to move one way, you need to shoot foam the opposite way.
Right.
Does that make sense, Ian?
I'm following this so far.
Yeah, so that's the idea of momentum conservation. There's another way to look at it, which maybe we can talk about that in respect to last week's episode, or last month's episode, whatever it was. Where
the previous episode.
Exactly. Where if you only think of him as the system, Wally as the system, or maybe Wally and the extinguisher as a system, right? Then you can think of that, and then the ejection of the foam is applying a force to him and the extinguisher, and that's why he's moving.
Sure.
Basically, and they're totally equivalent ways. You'll get the exact same answer both ways. That's kind of the cool thing about physics is there's multiple totally accurate ways to describe something, and some of them are easier than others to do at first given situation. But they all should agree because physics is self-consistent, which is nice.
Right.
As is most science, generally.
That's the thing about science.
That's the nice thing. Yeah. All right, Ian. So there's the concept.
Yeah.
Momentum conservation. Where do we see that in the world today?
Oh boy, it's all over. It's one of those big ones.
It's a big encompassing.
It's everywhere.
You did bring up very beginning of this topic a pretty
my favorite one, maybe
your favorite one,
which is rocket science. Right? I'm sure that's where you're getting to. When you think about how a rocket works, everyone's like, yeah, it shoots fire out the back. That's obviously how it works.
Blast off.
That's how jetpacks work. That's how everything works. So it just shoots fire out the back and it goes forward. But that's so reductive, Really what's going on is they're spitting out a ton of particles.
Right.
Much like Wally's fire extinguisher.
Just like you might.
And in fact, if you look at a fire extinguisher, it has a little nozzle on the front of it. And rockets also, if you pay close attention, have nozzles where they shoot their fire out from. So it's pretty much it's a microcosm of rocket science is what it is.
Yeah, exactly. All that, and it's worth pointing out, right? The faster you eject that fuel, right, you're giving that fuel more momentum downwards, right? Because it's the same mass no matter how fast or slow you eject it. So if you eject it slowly, it'll have some amount of momentum downwards. If you eject that same amount of fuel down quickly, like you do with rocket launches, right, that means you're shooting it down with a lot more momentum, which means, right, if you and the fuel have zero momentum initially, if that has a ton of momentum downwards, you're going to get the exact same amount of momentum upwards. So the faster the fuel goes out below you, the faster you'll go up above you. Great example, Ian.
Woo! Crushed it. I'm going home.
No, wait, come back.
Okay, I'm back. What do you got?
Sure. So I kind of mentioned air hockey tables. That's a great example, right?
That's a really good one.
Yeah.
That's a knockout.
Thank you. Another one that I think is pretty good is any kind of billiard ball collision, right? So in this way, right, if you think about the two billiard balls that are going to hit each other, right, one of them zooming towards the other one that's at rest. If you look at them both together as the system, right, then, and, there's very little friction on the table because they're rolling and they're smooth and all that fun stuff, right? It works really well on a felt table with smooth balls, right? Then those balls together, their momentum won't change, right? One of them is moving, let's say it's moving straight away from you when you first hit it with your cue stick, right? Moving straight away from you. That means the total net momentum of those two balls is still going to be going straight away from you even once they've collided, right? They might go off at two different angles, but if you look at those angles and look at their velocities in those respective directions and their masses, right, you'll find that they still combined have a momentum directly away from you in the direction the cue stick goes.
Right.
Yeah, which is super cool. And that's, how good pool players know how to play billiards, right? They know that that's the truth. So they hit it at the right angles to get the balls to share the momentum in just the right way, such that it goes the angle they want it to go in.
Right.
Yeah. Those are probably the most basic ones for me. Anything else you're right off the noggin?
So one that really popped into my head, and maybe you can help me translate this, because I think the way I'm going to phrase it is going to be a little more forces, less momentum. Have you ever had one of those little gardening hose attachments that converts your garden hose into, like, you can make it mist, or you can make it
like a beam
soak, or you can make it jet.
Yeah.
And when you use the jet mode versus like the soak mode, you can feel it push against your hand more.
Yeah.
And the water shoots out faster and further. Which I suppose, hey,
No,
that's momentum,
100%.
right?
That's the exact same idea as the rocket launch or Wally with the extinguisher, right?
I'm all about nozzles, apparently.
It's all about,
nozzles is my thing.
Nozzles and ejections, yeah. I mean, and it's a little hidden because you are holding it with your hand, right? So you're applying a force on the thing. But if you just had the nozzle standing up, unaided, right, and you launched out the mist, right, presumably there's the same flow rate, right, the same amount of liquid coming out, but the faster it comes out, right, same mass, but the faster it comes out, so the jet versus the mist, right, it'll launch it further backwards, right?
Right.
If it weren't being held by someone's hand.
If you had like the locking version,
Yeah.
and you locked it down, just dropped it on the ground, and it's like spraying everywhere, and like you can't get it because it keeps spraying you in the eyes. Yeah, classic.
Good old summertime.
Yeah, it's comedy gold right there.
All right. Well, I think that's all I can think of off the top of my head, at least. I mean,
Yeah, I
look
don't know about any
around,
other
analyze it
momentum.
yourself, right? This is a nice one you can kind of see anywhere you look, especially during collisions or things, like rockets. Like that stuff is it's all about momentum conservation.
I was trying to think of something good that applies to like winter time.
Well,
But
there's a
I
lot less
don't have
friction in
any.
wintertime on the roads, so
There is, but I don't have a way to convert that to
you could talk
a
about
good momentum example.
What about like a car when let's say there's an intersection, all right, and you want to turn left. If you try to turn left and you're going a little quick into the intersection and it's really icy out, you won't, because you won't be able to apply a force. So there won't be any external forces on you because your wheels can't grip on the ice. So without any external forces, to the left in this case, you're just going to keep going straight, the same direction you were already going in. There's a good example.
Your momentum is conserved.
Without any external forces,
Here's-
there will be no change in momentum. That's the law.
One time, I was tubing which I know we've had at least one listener not from Minnesota. Tubing is where you sit in a tire's inner tube and go down a hill. It's a classic wintertime activity. And I was at the bottom of a hill, and some dude came down in a tube and hit me. And he slowed down, and I got launched. So, boom, conservation of momentum.
Yeah, exactly. If you look at the momentum before the collision and after collision, it'll be the same.
Yeah. How about that? Until I hit the ground and tumbled.
Well, yeah, then an external force is applied.
Yeah, it sure did. Yeah, it sure did. I think that's what I got for momentum.
Nice.
Should we move on to questions from the audience?
Let's do it. What do we got?
Or do you want to give like a punchline first, like a wrap up? Or are you good?
I feel pretty good.
Great. Let's move on. This question has been a long time coming. We have not answered it in a while, but it's time to bite the bullet.
Let's do
And we've waited too long. I would have preferred to have it line up with an episode that made sense with it, but we don't. So here we are, folks. Get ready for this one.
Yeehaw.
From our good friend Amanda, please says, another question from me. Thanks for bringing all the questions, Amanda.
Love it.
We appreciate that. On my podcast's most recent episode, at Root Following, just a little plug there, we talked about Thor and the Bifrost, among other things. In Thor 2011, they mentioned an Einstein-Rosen bridge. Can you elaborate on what that is?
I can try.
Will?
Yeah.
Can you?
Boy, great question. So we talked about, I believe this question is probably from our relativistic time dilation episode. If I had to hazard a guess. And in there, I try to express as strongly as I could that I am not an expert at relativistic physics, especially not general relativity. I'm pretty good at special relativity. General relativity, you might be familiar, I talked about it there, is about the whole curvature of space-time itself. So like time gets wacky when there's a lot of mass or a lot of energy. Same thing with space, gets curved, and paths that are the shortest paths now are no longer straight paths that get curved. It's all kind of weird stuff. And an Einstein-Rosen bridge is basically an excellent example of how weird it can get. The basic idea is that of a wormhole, right? So it's the idea that two very separate points in space, time, in relativity, right? Two very different positions, locations, they can be quote-unquote linked via an Einstein-Rosen bridge. And I'm certainly not up on all the mathematics to understand it fully, but Ian, if you imagine 2 points on a piece of paper...
Jeez, every time.
Bend the paper. Yeah, I mean, I'm sure you're familiar if you watch Interstellar or a lot of other films where they go through wormholes. They usually have a classic analogy they use, or someone for some reason has a paper and pencil, even though they're on a space station. I don't know, and they're like, "Well, let's explain to the audience how wormholes work." And they always just have 2 points, and they say the fastest way between those 2 points on the paper is a straight line because that's how geometry works. But if you bend the paper onto itself, like a hamburger style, then those 2 points can directly be on top of each other. And then you traditionally poke a pencil through at those 2 points and you say, now there's a hole that you can go through that's faster than the straight line. And unfortunately, that's the best I'm going to give an explanation as well, because it's frankly a little over my head. The math gets pretty hairy and crazy, and it's pretty theoretical. I can tell you that obviously it's named after Einstein, which you're probably familiar with, but it's also named after Nathan Rosen, who was another physicist. I think in 1935 they worked together on a paper talking about, like, I think a field theory for electrons, which has since been worked out. And that, I believe, is where that name comes from, that paper. But I'm not an expert in that field. I hope that answers your question. The basic, quick answer is it's just a wormhole. As you've seen in most movies about wormholes, it's the whole idea.
It's just a buzzword for wormhole.
Well, I mean, if anything, wormhole is a buzzword for Einstein-Rosen bridge, and that's like the name.
Okay, hotshot.
Yeah. But yeah, the idea is it's this whole curvature of space-time being able to make 2 points that aren't traditionally near each other be much closer to each other.
Thanks, Will, for always taking on these hard questions, these hard hitters.
No problem. Don't keep them
Folks,
coming.
if you want to ask Will a question, you can do that by tweeting at us at Podcast Frames, or you can email us at referenceframespodcast@gmail.com. Or if you know me or Will in real life, you can talk to us, but we'll forget. So you should do those other things that I mentioned.
I would recommend that.
Also, huge news. I believe that Spotify has now opened up ratings for podcasts.
Oh, my.
So if you listen on Spotify, you probably have a Spotify account. You could rate our podcast. That'd be delightful.
Yeah.
That's all I have to say for the plug zone. Thanks for listening. Will, you got anything else you want to say on the way out? The outro?
No, other than it's good to be back in the booth recording again. We'll have some fun in the new year. And hope you guys all have a good new year. And please, bring us some questions or recommendations for episodes or fun ideas you think you'd like us to talk about. We're all ears.